this video will cover section 10.7, probability, and it will cover the second part of the section. The last problem we covered in problem 1 was the one about an event not occurring. And so that's when we used to do that 1 minus the event actually occurring. So if you need to review, you can watch the first part of the video. Now let's move on to the next one, and this one talks about when probabilities could happen, one or the other. And so right here we're going to refer to this as mutually exclusive events. And so what that means is that one event does not depend on the other. So what we do in probability, the word or, it represents addition. And using set notation, the same addition of probabilities will be represented by union. And that looks like a U, and it represents union. So what that means is, for example, if you consider all the cards that are red, let me give you a better example. Okay, so let's think about all the cards that are red again. And let's think about all the cards that are black. And so let's just pretend for a minute that, well, we don't need to pretend, it is a fact. Right here you will have your 2, your 3, your A's, your 4, your 5, your 6, your 7, 8, and your 9, and your 10. And so the cards that are black, same thing, we will have 8, 2, 3, 4, 5, 6, 7, 8, 9, 10. And let's put all the face cards, which will be the Jack, Queen, and the King, at the intersection. So if the problem was, so what is the probability that you get a face card that is either red or black, then we're actually looking at that intersection. And how many cards will be there total? 3 plus 3. And so that 3 plus 3 will give us 6 possibilities, because we don't care if it's red or black. We just want a face card. And so that will be an example of that. But let's see what the problem is asking here. Maybe that will make us understand better. Well, make you. I already know how. So let's see. So if one card is randomly selected from a deck of cards, what is the probability of selecting a king or a queen? So we're talking about the following. What is the probability of getting a king or a queen? And so we have the word or. So what we know that what needs to be done is calculate the probability of getting a king plus calculating the probability of getting a queen. And remember, these two events are mutually exclusive. They have nothing to do with each other. So the probability of getting a king will be, how many kings are there? We have 4 suits, so that will be 4 out of 52. How many queens are there? And that will also be 4, one of each suit, out of 52. And so here we will have 8 divided by 52. And of course, we could simplify it, and that will be 4 out of 26. And we could divide by 2 again, so that will be 2 divided by 13. Okay, so let's move on. And just remember, actually, if you don't have the definition, please go ahead and copy it. Thank you, Miguel, for writing them down. So mutually exclusive events are two events if any two events A and B occur simultaneously. Okay. So I'm actually going to correct the definition here. So I'm going to say that they cannot occur simultaneously. Think about this. If you get a card and you're hoping to get a face card, then you're going to get either a queen or a king or a jack, but you cannot get all three at once. And so because of that, we will say cannot occur simultaneously. So those are mutually exclusive events. The one does not depend on the other. Let's go to the next slide. And now here we're going to do the same thing. Oh, look, here there's a diagram, a Venn diagram of what I was trying to show you earlier. So let's see, the question says, consider the deck of 52 cards shown in that figure. Suppose that these cards are shuffled and you randomly select one card from the deck. What is the probability of selecting a diamond or a picture card? And remember, picture card, face card, that will be the jack, the queen, and the king. Diamond card, that will be including face cards or picture cards and the numbers, and of course the ace. So in this case, we're going to be talking about events that are not mutually exclusive, and so what that means is that those events can occur at the same time. So what do we mean by that? So imagine, and we're talking about diamonds of that suit, and we have the drawing here. All those diamonds, we have the numbers, but we also have the face cards right there. And of course, there are other face cards, which will be the jack, the queen, and the king of clubs, the jack, the queen, and the king of hearts, and the jack, the queen, and the king of spades. But, so we could say that this set is just the set of diamonds, and this set is the set of picture cards. It's actually written there for us. And so our intersection is right here. The ones that are diamonds, and they're also face cards. So these are actually the events that will be mutually exclusive. I'm sorry, not mutually exclusive. That means that if it is a jack, a queen, or a king of diamonds, they will fall into both sets, the set of diamonds and the set of picture cards. So what do we need to do here? So if you think about getting a card that is a diamond or, remember it says or, a picture card, we're going to start by the same way. So the probability of getting a diamond, actually let's write it first, diamond or a picture card. So for that, it will be the probability of getting a diamond plus the probability of getting a picture. So if we calculate those, we know how many diamonds are in a deck of cards, and so there are 13 out of 52. How many picture cards are in a deck of cards? And that will be 4 for each suit, the jack, the queen, and the king. I'm sorry, 3, jack, king, and queen, times 4, because we have 4 different suits, so 3 times 4 will be 12. And so we have 12 picture cards in a 52 card deck. Now, because those events are not exclusive, meaning they're here in the intersection, we're actually accounting for them twice. We're counting those 3 here. 3 out of those 13 are those face diamond cards, and 3 out of these 12 are actually face diamond cards as well. Remember, these were all the diamonds, and these were all the picture cards. So out of those 52 cards, 13 are diamonds, but 3 are face and diamonds. Now we look at the other one, and this fraction represents the picture cards. Out of a deck of 52 cards, 12 are picture cards, and 3 of those 12 are both, they're picture and they're diamonds. So what we're doing here is we're counting these ones twice. It's like if we were saying this. So what we need to do is subtract them once. So what we're going to do is subtract how many were at the intersection originally. And so that will be this 3 that I was talking about. So now we're going to put all of them under one fraction if you want to. So 13 plus 12 minus 3, everything over 52. So we will have 25 minus 3, so that will be 22 over 52. And of course, we can divide by 2, so that will be 11 divided by 26. And so that will be our final answer. Okay, so now let's look at the formula for both mutually exclusive and not mutually exclusive. So, I'm sorry, this is just not for not mutually exclusive, so it covers the formula of the problem we just worked out. Remember the one where the diamonds were also face cards, right here. This is the intersection. So when we look at the formula, what I did was to find, if we have the word or, it implies addition. But in this case, the events can occur at the same time. A card could be red, and it could also be a diamond. So because of that, we have to subtract that intersection. And so that's what I did by subtracting 3 over 52. So intersection, the symbol for it is like an inverted U. That will mean intersection. And this one right here will mean union. All right, so let's go to the next slide. We're almost done. So example 6. And more probability with events that are not mutually exclusive. So we have that figure on the right side, and it illustrates a spinner. It is equally probable that the pointer will land on one of the 8 regions, number 1 through 8. If the pointer lands on a borderline, you have to spin again. Find the probability that the pointer will stop on an even number or a number greater than 5. So let's write it down. So what is the probability of getting an even number or a number greater than 5? So I'm going to break this down into 2. We have 4, so that would be imply addition. So what is the probability of getting an even number plus the probability of getting a number greater than 5? So you can tell right away that with the numbers 1 through 8, there are going to be some intersections, meaning there are some numbers that could be both. They could be even and they could be greater than 5. So let's see if we can find those numbers. So let's see. Even numbers, we have 2, we have 4, we have 6, and we have 8. But out of those 4 even numbers, how many of those are greater than 5? And the answer will be 6 and 8. Only 2 of them. So let's see. The probability that you get an even number, how many even numbers are there? We have 2, 4, 6, and 8. So we have 4 out of a total of 8. Plus the probability of getting a number that is greater than 5. And so that will be 2. I'm sorry, just greater than 5, that will include 6, 7, and 8. So that is 3 over 8. Now we're talking about events that could occur at the same time, meaning the number could be greater than 5 and also even. So it only makes sense, and I'm going to have to write it here because I ran out of space, that we subtract the probability of both of them occurring together, meaning even and greater than 5. So that's what I'm going to subtract here. So the number is 6 and 8. Those two numbers are even and also greater than 5. So 2 over 8. So let's see. We have 4 plus 3 minus 2. Everything divided by 8. That will be 7 minus 2 is 5. So 5 eighths. Now for the checkpoint, to find the probability that the pointer will stop on an odd number or a number less than 5, we have 4 numbers that are odd, and we have 4 numbers that are less than 5. And how many numbers do we have that are both less than 5 and odd? So that will be 3 and 1. So that will be 2 out of 8 possible numbers. So here we have 4 plus 4 minus 2 over 8. So that will be 6 over 8, which is 3 over 4. So let's move on to that next problem. And we have here on this example, probability with real world data. So the table shows the marital status of the U.S. population in 2010. Numbers in the table are expressed in millions. So we have here, by gender, we have male and female. And so out of those male and females, 65 were married and 65. And so the total will be 130. Now, if we look at the second column, we have 40 males who were never married and 34 females who were never married. So the total was 74. If we look at the third column, that would be the divorced people, and there were 10 males and 14 females. And the next column, there were 3 males and 11 females in the widowed column. Total 14. And let's keep that in mind, we're talking about millions, guys. So the total, now if we add the rows, we already added the columns, so it's already there for us. And if we add the rows, like in this way, if we add all the males, we had a total of 118 males, and we had a total of 124 females. So if one person, and the total of all combined is 242. You can get that 242 by adding the males and the females, or by adding all of this marital status of all of the sample states. So if one person is randomly selected from the population represented in the table, find the probability that A, the person is divorced or male. And so for a person to be divorced or male, it will have to be here. So that will be 10 out of 242. But if we use the probabilities, we should be looking for a person who is divorced or male. And if I do that, I should be looking for a person who is divorced. What's the probability of a person to be male? And of course, we need to subtract that intersection where they're both divorced and male. And that was that. Male and, remember when we use the word and, that means intersection. Okay, so out of all the divorced people, there were 24. 10 of them were male. I'm sorry, that is wrong. I shouldn't do that. So out of the total of people of the sample space, which is 242, 24 were divorced. I'm looking at this number right here. Now, out of the whole sample space, 242, how many were males? And that will be 118. Now, we know that these two events are mutually exclusive, are not mutually exclusive. That means they could happen at the same time. So, how many do we have that are both divorced and male? And so that will be 10 out of the grand total of 242. So, if we have 24 plus 118 minus 10 divided by 242. So that will be that will be 132 divided by 242. And if we reduce this, we will get 6/11. And as a decimal, approximately 0.55. So what you see here, the person is divorced or male, this is not correct. That is the answer for something else. And that something else is actually going to be, the question was something around what is the probability that a person selected from that group will be both divorced and, you guys see the difference, or and male. And so if we were just to calculate that, it would be enough for us to look at that 10, where both things happen, divorce and male. Okay, so let's go to the next one. Oh, what happened? Okay, so we'll move to the next one after that. And so we have here probabilities with independent events. So two events are independent. So please copy the definition. Two events are independent if the outcome of one event does not influence the other. So right here, what we are going to do is we have the word and so that will imply multiplication. And remember, this is for independent events. So this is another very popular game in Vegas, continuing with our Vegas theme. So for this one, people bet on a number and they also bet on a color. I've never played this one, so I can't really explain it that well. But let's see. We have the figure, shows a US roulette wheel that has 38 number slots, 1 through 36. But we also have a 0 and a double 0, so that's why there are a total of 38 numbers. Of the 38 compartments, 18 are black, 18 are red, and 2 are green. A play has the dealer spin the wheel and a small ball in opposite directions. As the ball slows to a stop, it can land with equal probability on any one of the 38 number slots, assuming the machine has not been tampered. Find the probability of red occurring on 2 consecutive plays. So right here, this is our key to know that these 2 events are independent of each other, because this is what happens. The dealer will spin the wheel once, he or she will wait for the ball to stop, and then he or she will spin the wheel again, and so the outcome of the first spin doesn't really matter the outcome of the second. So let's see, the question says that you will get red twice consecutively. So let's see, how many compartments do we have that are red? We have 18 out of 38. So we want to get the probability of getting red and getting red again. So remember, and implies multiplication and probability. So we're going to get the probability of getting red the first time, and then we're going to multiply by the probability of getting red a second time. So here we will have 18 out of 38 times 18 out of 38. So we multiply them, and we're going to get something like, actually I'm going to give you guys the reduced form. So that will be 81 over 361. And decimal approximation, we're going to use 0.224. That will be the probability, around that 22.4%. So it's actually not that bad. All right, now let's look at this picture. Let's look at this lovely family. And I bet you if you were the guy on the picture, you wouldn't be as happy as he is, because this guy was lucky enough to have 9 girls. Imagine that. 9 girls plus your wife. 10 women in a house. So, let's see, look at the picture. I already told you what's going on. Find the probability that that could happen. Like, how lucky or unlucky was this guy? Let's see. So, every time you have a kid, and right here we're only going to consider, for the purpose of this lesson, 2 genders, male and female. However, there are other genders, but we're not going to get into that right now. So, assume that every time a woman gets pregnant, she could have only a boy or a girl. And when I say there are other genders, I am referring at some people who are actually born with both genitalia. So, we're not only going to consider 2 choices, like heads and tails. So now let's see. The first time, he had, out of 2, he had a girl. So he had a 1 over 2. Second time, same thing. Third time, 4th time, 5th time. And I really don't know why they kept trying. But I guess this used to happen back in the day. 1, 2, 3, 4, 5, 6, 7, 8, and 9. And so, of course, we're smart enough to notice that this is an exponential quantity, because both the 9 is being multiplied by itself 9 times, and the 2 is multiplied by itself 9 times. And of course, this could also be represented as this. Or we could also say, well, 1 to the 9th power is just 1. And so what is 2 to the 9th power? And so that will be 512. So that is the answer for this question, and also the video. Um, it is important to mention that this event of having a boy or a girl is very independent of each other. If you have siblings, you could see that just because you're a girl doesn't mean that the next baby will be a boy or vice versa. So that's why they are independent, and that's why we can solve that type of problem by multiplying all the probabilities. So this is the end of the video. Make sure you do your homework and have fun, but only a little bit, not too much.